This problem might look daunting at first with all the different charges and dots, but one thing that makes this problem much easier is understanding the concept of symmetry, and how charged particles that are equidistant from points will cancel each other out if they have the same magnitude and sign. Let's look at diagram 1 of this, for example. We can see that the first charge is a positive E, and on the exact other side of that central point, at the exact same distance away, is another positive E. Now think about how the electric field behaves. Recall that, according to convention, electric field lines point away from positive charges and towards negative charge. So at this central point, there is going to be, from the leftmost positive charge, an electric field line pointing to the right, emanating away from that positive charge. However, there is also going to be, from the rightmost particle, another electric field line pointing to the left, again, away from the rightmost charge. Since these two charges have the same distance from the central point, the magnitude of the force they exert, the magnitude of their electric fields, are equal, but since they're pointing in the opposite directions, their effects cancel out. So one thing we can do to simplify our analysis of this diagram is to just look for symmetrical dots and cancel them out completely, and they can just be ignored during our analysis. Let's continue on with the first part of the diagram. So there's a negative charge and a negative charge. Again, both have the same distance away from the central point. So they can be canceled out because they're negative charges, so the electric field line would be pointing towards those charges. So from this one, there'd be an electric field pointing to the left. From this one, there'd be an electric field pointing to the right. And again, it's easy to see that they would cancel each other out. So all the charges have canceled out, which means that the net electric field at this central point is just 0. Next, let's look at the second section of the diagram. So this time it doesn't look like there's anything symmetrical. There, on the leftmost side, we have a positive charge, so that's going to create an electric field line pointing to the right. We have another positive charge, it's going to be another field line pointing to the right. Two negative charges on the right-hand side, that's going to be two more electric field lines pointing to the right, because again, the electric field lines point towards negative charges. So there's actually a pretty strong electric field magnitude with the second part. Let's look at the third one now. We've got we do have a pair of symmetrical charges, because these positive charges toward the middle will cancel each other out. But the ones on the outer won't. This leftmost negative charge will create an electric field line pointing to the left, and the rightmost electric point will create an electric field, again, pointing to the left, away from that positive charge. And for the final section of the diagram, we have a pair of symmetrical charges. These negative charges will cancel out, because they're the same distance apart and the same sign. These inner charges won't, however. From the leftmost negative one, there's going to be a field pointing to the left, and from the rightmost positive one, again, an electric field pointing to the left. So now that we've kind of analyzed the electric forces from the field on each part of the diagram, now let's get to actually ranking them. And keep in mind that the problem is only asking us to rank the magnitudes, so we don't need to worry about the signs or figuring out if one is smaller because it's leftmost and pointed negatively as opposed to another. We're only worried about the magnitudes, which means that since part 1 of the diagram has an electric field magnitude of 0, that means that 1 is certainly going to be at the bottom of our ranking, because there's no net electric field there at all. We can sort the other ones by looking at the number of arrows, the number of field lines we've put at the center. Because remember that the electric field's strength is proportional to the density of electric field lines at that point. And we can see that in the second diagram, we've got 4 lines, and in the third and fourth ones, we each have 2 lines. So because the second one has 4 lines at the center, that means that 2 is going to have the largest magnitude of the net electric field strength. So now we have to rank parts 3 and 4. They both have 2 arrows, so you might think that they're equal to each other, because it's the same number of electric field lines. But it's important to remember that there are still other ways that we can measure and rank the strength of those fields. Notice that the fourth subdiagram the electric field lines are created by two charges that are closer to the center than in the case of the third subdiagram, where the electric field is created by two that are farther apart. Remember that the formula for electric field lines, the formula for the electric field states that the strength of the field is inversely proportional to the square of the distance between the charge and the point we're analyzing. So because the charges in the subdiagram 4 are closer together, that means that their strength is actually going to be a bit higher than the charges in the third subdiagram, where the point charges are farther apart. So that means that the fourth subdiagram has a higher magnitude of the electric field than the third one. So our total ranking is that 2 over 4 over 3 over 1. And that is our answer to this problem. I hope this video helped you out. If it did, please consider donating to my Patreon or subscribing, as that'll help me out in making more videos just like this. If you have a request or a question, leave a comment down below, and I hope you all have a lovely day. Bye-bye.